Based on your Chapter 1 outline, here's a breakdown of key content and considerations for each section, incorporating the step notations. Chapter 1, Introduction. Overall purpose. Set the stage. Convince the reader the research is necessary, important, and clearly defined. Flow. Start broad, background, narrow down to the specific gap, problem statement, explain why filling it matters, significance, define the boundaries, scope/delimitations, and preview the journey. Outline. 1.1 Background, Infrastructure Performance Challenges. Step 3, Purpose. Establish the context and importance of infrastructure performance. Key content. Define infrastructure performance in your context, e.g., transportation networks, water systems, energy grids, bridges. Discuss the critical role of infrastructure in society/economy/safety, e.g., economic productivity, public safety, quality of life, sustainability. Highlight the major challenges facing infrastructure systems, aging assets and deterioration. Increasing demand and capacity issues. Climate change impacts, resilience. Funding constraints and life cycle costs. Consequences of poor performance, failures, delays, economic losses, safety risks. Introduce the need for effective performance assessment and management. Why? Step 3, this establishes the broader context before diving into the specific problem with current assessment methods. It answers why should anyone care about infrastructure performance at all. 1.2 Problem statement, limitations of current assessment methods. Step 1, Purpose. Clearly define the specific gap in knowledge or practice that your research addresses. This is the core why of your thesis. Key content, briefly describe common or standard methods used to assess infrastructure performance, e.g., visual inspection, specific indices, sensor networks, specific models. Critically identify their limitations. Be specific and evidence-based. Examples: data issues, reliance on sparse/infrequent/inaccurate/manual data collection. High cost of data acquisition. Methodological issues, oversimplification, ignoring interdependencies, uncertainty. Lack of predictive capability. Inability to handle complex scenarios, e.g., climate extremes, cascading failures. Subjectivity, e.g., in visual inspections. Inability to integrate diverse data types. Static versus dynamic needs. Practical issues, time-consuming, resource-intensive, disruptive to operations. Difficulty in translating assessment results into actionable maintenance/management decisions. Lack of real-time or near real-time capability. Poor scalability. Articulate the gap. State clearly what current methods cannot do effectively, or what critical aspect they overlook, that your research will address. E.g., current methods lack a robust framework for integrating real-time sensor data with predictive deterioration models to proactively manage network-wide resilience under climate uncertainty. Consequence. Briefly reiterate the negative impact of not addressing these limitations, linking back to 1.1 Challenges. Why? Step 1, this is the fundamental driver of your research. Identifying the precise problem is logically the first step in defining what you need to solve, even if you write the background section first for narrative flow in the final document. 1.3 Significance of the research purpose. Answer: so what? Explain the value and potential impact of your research. Key content, theoretical contribution. How will your research advance knowledge? E.g., develops a novel assessment framework, proposes a new model/algorithm, integrates disparate theories, provides new insights into performance dynamics. Practical contribution. What real-world benefits might it bring? Improved decision-making for asset managers/owners. Enhanced safety and reliability of infrastructure. More efficient allocation of resources, cost savings. Better prioritization of maintenance/renewal. Increased resilience to shocks/stresses. Development of new tools or methodologies usable by practitioners. Stakeholder benefits. Who specifically benefits? E.g., government agencies, infrastructure operators, engineers, the public. Broader impact. Contribution to societal goals, sustainability, economic development, climate adaptation. 1.4 Scope and delimitations. Purpose. Define the boundaries of your research. What you will and will not do. Manages reader expectations. Key content, scope, what is included. Specific infrastructure type, studied, e.g., highway bridges, urban water distribution networks. Specific performance aspects / metrics focused on, e.g., structural integrity, hydraulic capacity, travel time, reliability, resilience index. Specific assessment methods or data types you are developing / using. Geographic or case study limitations, if any. Time frame considered, e.g., current state, future projections under specific scenarios. Delimitations, what is not included, justified choices. Aspects explicitly excluded, e.g., does not include economic valuation of benefits, focuses on physical performance, not organizational management, uses simulated data for X phase, not field data. Crucially, state the reason for each delimitation, e.g., beyond the core focus of this engineering study, requires expertise beyond this research, limited by data availability, to maintain feasibility within project constraints. 1.5 Research outline. Purpose. Provide a roadmap for the reader. Show the structure and logical flow of the entire thesis. Key content. Briefly list each subsequent chapter and its primary purpose / content. Chapter 2, Literature Review. Comprehensive review of existing research on infrastructure performance, assessment methods, relevant models, and identified gaps. Chapter 3, Methodology / research design. Detailed description of the methods used to address the problem, data collection, model development, analysis techniques, case study selection. Chapter 4, e.g., model development / framework design. Presentation of the core theoretical or methodological contribution of your research. Chapter 5, case study / application / results. Application of your methodology to a real or simulated case study. Presentation and analysis of findings. Chapter 6, discussion. Interpretation of results in relation to the problem statement and literature. Discussion of implications, limitations of your approach, and practical applicability. Chapter 7, conclusion and recommendations. Summary of key findings, reiteration of contributions, answer to the research problem, and suggestions for future research and implementation. Key considerations for writing, clarity and conciseness. Be direct and avoid unnecessary jargon. Define key terms when first used. Logical flow. Ensure each section leads naturally to the next. Background, problem, why it matters, what you'll do, how the thesis is structured. Justification. Especially important for problem statement, limitations must be credible, and scope / delimitations, exclusions must be reasoned. Significance. Go beyond. It's important. Be specific about how and to whom. Target audience. Write for an informed academic audience familiar with the general field but not necessarily your specific niche. Provide sufficient context. Step notations. While step 1, problem, is the intellectual starting point, placing the background, step 3, first in the chapter, creates a more natural narrative flow for the reader. This is perfectly acceptable. The steps likely reflect your thinking / development process, not the final document order. This structure provides a solid foundation for a compelling introduction chapter that clearly motivates and defines your research. Good luck! Based on your Chapter 2 outline, here's a detailed breakdown of content, purpose, and strategic considerations, incorporating the Step 6 notation and building on Chapter 1, Chapter 2, Literature Review, Step 6, Overall Purpose. To demonstrate your comprehensive understanding of the field, critically evaluate existing knowledge, identify the specific niche your research occupies, and justify the need for your proposed approach. It synthesizes what is known and where the knowledge falls short. Flow. Start with established domain-specific models. 2.1, 2.2, critically analyze their shortcomings. 2.3, linking back to CH1 problem, then explore emerging solutions. 2.4, to set the stage for your methodology. Why? Step 6, the literature review logically follows defining your problem. Step 1/CH1.2, and understanding the broader context. Step 3/CH1.1. It allows you to explore existing solutions. Steps 4 and 5 would be exploring potential solutions, and formally identify the specific gap our research will fill, based on a thorough analysis of prior work. It grounds your research in the academic conversation. 2.1 Existing models for road performance, e.g., Pavement Condition Index, HDM4, purpose: provide an overview and critical analysis of established methods for assessing road infrastructure performance. Key content: model types categorize, e.g., empirical, mechanistic empirical, deterministic, stochastic, network level, project level. Specific models: Pavement Condition Index, PCI. Explain methodology, visual inspection, distress types, weighting, calculation, strengths, simplicity, standardization, wide adoption and limitations, subjectivity, snapshot view, limited predictive power, focus on surface. HDM4, Highway Development and Management Model. Explain its purpose, economic evaluation, life cycle costing, prioritization, core components, deterioration models, user costs, optimization, strengths, comprehensive framework, economic focus and limitations, complexity, data intensive, calibration challenges, potentially outdated models. Other key models. Briefly mention others relevant to your focus, e.g., International Roughness Index, IRI, for ride quality, Mechanistic Empirical Pavement Design Guide, MPG, models, specific performance prediction models. Data sources and methods. Discuss common data inputs, visual surveys, roughness measurements, deflection testing, traffic counts, and collection methods. Critical analysis. Don't just describe. Evaluate each model's applicability, accuracy, data requirements, ability to handle modern challenges, resilience, sustainability, and limitations relevant to your problem statement. CH1.2. 2.2 Existing models for building performance, e.g., structural health monitoring, FEA, purpose: provide an overview and critical analysis of established methods for assessing building infrastructure performance. Key content: model types categorize, e.g., visual inspection protocols, non-destructive testing, NDT, structural health monitoring, SHM, analytical/computational models, performance-based design frameworks. Specific approaches: structural health monitoring, SHM. Explain the paradigm, sensor networks, data acquisition, feature extraction, damage diagnosis/prognosis. Discuss sensor types, strain gauges, accelerometers, fiber optics, data analysis methods, modal analysis, outlier detection, strengths, continuous monitoring, potential for early warning, objective data and limitations, cost, installation complexity, data management, interpreting results, environmental effects. Finite element analysis, FEA. Explain its basis, numerical simulation of structural behavior under loads, applications, design verification, assessment of existing structures, failure analysis, strengths, detailed stress/strain prediction, scenario testing and limitations, model complexity/uncertainty, computational cost, requires expert knowledge, input data quality dependency. Other key models/methods: building condition assessments, BCA, protocols, specific deterioration models, e.g., for concrete carbonation, steel corrosion, fragility curves for seismic performance, energy performance models, if relevant. Critical analysis: evaluate strengths and weaknesses, focusing on limitations related to predictive capability, real-time assessment, handling uncertainty, integration of diverse data, scalability, and cost-effectiveness. Again, linking back to CH 1.22.3. Gaps in current modeling approaches. Purpose: synthesize the critical limitations identified in sections 2.1 and 2.2 to explicitly define the research gap your study will address. This is the core OUTPUTOF, the literature review. Key content: synthesize and elevate cross-cutting limitations. Identify limitations common to both road and building assessment, or relevant to infrastructure broadly. Data-driven gaps: reliance on sparse, infrequent, manual, low-resolution, or subjective data. Challenges: integrating heterogeneous data, sensor and inspection and environmental, data scarcity for certain failure modes or new materials. Model-driven gaps: oversimplification of complex physical processes / interdependencies, limited ability to handle uncertainty / randomness, poor predictive capability, especially long-term or under extreme events, static models versus dynamic systems, lack of adaptability / learning, computational inefficiency for large-scale networks, difficulty quantifying resilience / sustainability. Practical gaps: high cost of implementation, sensors, computation, expertise, lack of real-time or near real-time actionable insights, difficulty translating model outputs into clear maintenance / management decisions, poor scalability from asset level to network level, limited focus on life cycle cost optimization under uncertainty, challenges in validating complex models. Domain-specific gaps: highlight critical gaps unique to roads or buildings if crucial to your specific problem. The gap statement: clearly and concisely articulate the specific knowledge gap or methodological shortcoming that your research will target. This must directly align with and refine your problem statement, CH 1.2, and set the stage for your proposed solution. Example: while significant advances exist in both road PCI/SHM and building SHM/FEA, current approaches lack a scalable, data fusion framework capable of integrating real-time sensor data, inspection records, and environmental factors within a probabilistic ML model to provide predictive, network-level resilience assessments for aging infrastructure under climate uncertainty. 2.4 Advances in computational methods, ML, AI, statistical modeling. Purpose: explore emerging computational paradigms that offer potential solutions to the gaps identified in section 2.3. Position your research within these advances. Key content: focus on relevance to infrastructure assessment, machine learning, ML/artificial intelligence, AI relevant techniques, supervised learning, regression, deterioration prediction, classification, damage detection, unsupervised learning, clustering, pattern discovery in sensor data, anomaly detection, reinforcement learning, optimizing maintenance decisions, deep learning, CNNs for image-based inspection / video analysis, RNN/LSTMs for temporal sensor data, GNNs for network level interdependencies. Applications: highlight specific examples in infrastructure literature, e.g., CNN-based crack detection from inspection images, LSTM models for predicting pavement roughness progression, Bayesian networks for probabilistic risk assessment of bridges, GNNs for traffic flow prediction influencing road wear. Potential: emphasize capabilities relevant to the gaps, handling complex data, pattern recognition, predictive modeling, uncertainty quantification, via Bayesian ML, adaptability, automation. Advanced statistical modeling, relevant techniques, Bayesian inference, updating beliefs with data, quantifying uncertainty, survival analysis / time to event models, predicting time until failure / maintenance, spatial statistics, modeling geographically correlated deterioration, multivariate analysis, stochastic process modeling. Applications: Bayesian updating of bridge reliability using SHM data, Weibull models for predicting remaining service life of pavements, geostatistical interpolation of sparse inspection data. Hybrid approaches discuss the power of combining physics-based models, e.g., simplified FEA, deterioration mechanics, with data-driven methods, ML/stats, for improved accuracy, interpretability, and generalizability, e.g., physics-informed neural networks, PINs. Critical evaluation. Don't just hype. Discuss challenges of these methods, data requirements, quality/quantity, black box nature, interpretability/explainability, model validation difficulties, computational cost for complex models, overfitting risks, need for domain expertise in application. Strategic considerations for Chapter 2, 1. Synthesis over summary. Avoid just listing studies. Analyze, compare, contrast, and identify trends, conflicts, and convergences in the literature. Group similar studies thematically. 2. The golden thread. Continuously link back to your problem statement, ch 1.2, and forward to your methodology, ch 3. Explicitly state how identified gaps justify your research question and approach. Section 2.3 is pivotal for this. 3. Critical voice. Maintain a critical stance throughout 2.1, 2.2, and 2.4. Question methodologies, assumptions, limitations, and generalizability of existing work. 4. Focus on relevance. In 2.4, focus only on computational methods directly relevant to solving the infrastructure assessment gaps. 2.3. Don't get sidetracked by generic AI explanations. 5. Use tables/matrices. Consider tables summarizing key models, 2.1, 2.2, with their core principles, inputs, outputs, strengths, weaknesses. A gap analysis matrix linking limitations from 2.1/2.2 to the specific gap categories in 2.3. Computational methods, 2.4, mapping techniques to potential infrastructure applications and addressed gaps. 6. Define terminology. Clearly define technical terms, acronyms, PCI, HDM4, SHM, FEA, CNN, LSTM, GNN, Bayesian inference, and key concepts upon first use. 7. Cite authoritatively. Use high-quality, peer-reviewed sources, journals, conference proceedings, reputable reports. Ensure citations support your analysis and claims about gaps/advances. 8. Conclude the chapter. Briefly summarize the state of the art, reiterate the critical gap, your research addresses, linking 2.3 back to ch 1.2, and state how the advances discussed in 2.4 provide the foundation for your proposed solution, leading into ch 3. This structure ensures your literature review isn't just a catalog of past work, but a powerful argument demonstrating why your specific research is necessary, novel, and positioned to make a valuable contribution. Good luck. Based on your Chapter 3 outline and its placement after the literature review, Step 6, here's a structured breakdown incorporating Steps 4 and 5, aligning objectives with the identified gaps, and formulating testable hypotheses. Chapter 3, Research Objectives and Hypotheses, Steps 4 and 5, overall purpose. To clearly define what the research aims to achieve, objectives, and state testable predictions, hypotheses, about the outcomes. This chapter translates the identified problem, ch 1.2, refined by ch 2.3, and potential solution avenues, ch 2.4, into a concrete research plan. Why Steps 4 and 5? Step 4, define solution approach. This step involves outlining how you intend to solve the problem. Your primary and secondary objectives represent this, defining the core actions and components of your proposed solution, developing integrated models, formulating degradation equations, integrating factors, validating. Step 5, formulate hypotheses. This step involves making specific, testable predictions about the expected outcomes of your solution approach. Hypotheses state what you believe will be true if your proposed models/methods are effective. 3.1 Primary objective: develop integrated mathematical models for road and building performance. Purpose states the overarching goal of the research: creating a unified modeling framework. Key considerations: integrated is crucial. Emphasize how the models integrate aspects missing in current approaches, per ch 2.3 gaps. Examples: integration of different physical processes, e.g., material degradation and environmental impact and structural response. Integration of data types, e.g., sensor data and inspection records and environmental data. Integration of performance aspects, e.g., structural integrity and functional serviceability. Integration across infrastructure types, identifying common mathematical principles for degradation in roads and buildings. Mathematical models specifies the approach indicates a quantitative, equation-based framework, likely leveraging advances from CH 2.4, ML, stats, hybrid. Hypotheses related to the primary objective, H1. The developed integrated mathematical model will provide a more accurate prediction of infrastructure performance degradation over time compared to standard single-focus models, e.g., PCI alone for roads or basic FEA without degradation for buildings. Tests overall superiority, H2. The integrated model framework will successfully quantify the synergistic effects of environmental stressors, e.g., freeze-thaw cycles, humidity, and mechanical loads on both road pavement, asphalt/concrete, and building structural elements, concrete/steel. Tests integration capability, 3.2. Secondary objectives and associated hypotheses. Objective 1, formulate degradation models for asphalt/concrete. Purpose: focus on the core material level deterioration processes fundamental to both road pavements and building structures. Key considerations: specify the type of degradation models, e.g., physics-based differential equations, data-driven ML regression, stochastic processes, hybrid. Define key degradation mechanisms, e.g., fatigue cracking, rutting, spalling, corrosion-induced cover cracking, carbonation. Indicate if models are unified, one model structure adaptable for both materials, or specific, separate but integrated models. Hypotheses: H1.1. The formulated asphalt degradation model will predict fatigue cracking progression with an accuracy, e.g., R superscript 2 0.85, May 2 mm, exceeding industry standard empirical models, e.g., those in MUPC, when validated against field data. H1.2. The formulated concrete degradation model for corrosion-induced cover cracking will accurately capture the time to cracking initiation and crack width propagation under varying chloride exposure conditions, validated against accelerated lab testing data. Focuses on a specific mechanism. H1.3. The degradation models for asphalt and concrete will share a common mathematical structure based on, e.g., damage mechanics principles, stochastic processes, demonstrating transferable core principles. Tests the integration aspect at the material level. Objective 2, integrate environmental and load stress factors. Purpose: explicitly incorporate the key external drivers of degradation identified in the background, CH 1.1, and literature gaps, CH 2.3, into the core degradation models. Key considerations: define specific environmental factors, e.g., temperature range/cycles, precipitation/humidity, freeze-thaw cycles, chemical exposure, de-icing salts, CO2. Define specific load stress factors, e.g., traffic load spectra/ESALs for roads, live/dead loads, wind loads, seismic loads for buildings. Specify how integration occurs mathematically, e.g., as input variables, modifying degradation rate parameters, within a coupled simulation framework. Hypotheses: H2.1 explicitly incorporating localized temperature fluctuations and moisture content as dynamic inputs will significantly improve the predictive accuracy, e.g., reduce RMSE by 15%, of the asphalt rutting model compared to models using average annual climate data. H2.2 integrating realistic traffic load spectra, including overloads, into the concrete fatigue model will reveal significantly higher degradation rates in specific bridge deck locations compared to models using only design load assumptions. Focuses on impact of integration. H2.3 The sensitivity analysis of the integrated model will identify specific environmental factor, e.g., freeze-thaw cycles as the dominant driver of degradation for specific infrastructure element, e.g., bridge approach slabs in cold climates. Tests model insight generation. Objective 3, validate models against real-world data. Purpose: provide empirical evidence to test the accuracy, reliability, and practical utility of the developed models. Key considerations: specify the source of real-world data, e.g., long-term PMS data for roads, SHM data from instrumented buildings, targeted field inspections, laboratory accelerated testing mimicking field conditions. Define the validation metrics, e.g., R-squared, RMSE, MAPE, prediction bias, confusion matrix for classification aspects, reliability indices. Define the benchmark S for comparison, e.g., performance of existing models like PCI prediction.